Instead of representing them using a 2D adjacency matrix, we are now going to represent them using 3-column matrix. Okay, now how to represent? So the first thing that we will represent, that is the value of the original adjacency matrix. It means how many rows, then how many columns, and how many non-zero values. So this is the first element, first row of this representation. Okay, this is the first row. Then in the second row, so we will represent the first non-zero value. So this is the first non-zero value. What is the row and column position of this non-zero value? This is the row position and this is the column position. So we will represent them 0, 1, and the value of the weight. Suppose this is weighted matrix, then instead of 1 there will be some value. So we will represent that. Suppose the value is W1. This is W1, this is W2, this is W3, this is W4, this is W5, this is W6. Then there the W1. In the next element or next row, it will represent the next non-zero value. So this is the next non-zero value. What is the row value of this non-zero value? 0. And what is the column value? 3. So I will represent them 0, 3, W2. Okay. Similarly, for the next element, next non-zero value. So this is the next non-zero value, W3. What is the row value? 1. What is the column value? 2. So I will represent it by 1, then 2, then W3. Then the next W4. What is the row value? 1. What is the column value? 4. W4. So this is the next element of this matrix. Okay, 3-column matrix. Then the next element, it will be for W5. What is the row value? The row value is 2. What is the column value? 3. So 2, 3, W5. This is the next element of this 3-column matrix. Then finally the last value, W6. What is the row value? 3. What is the column value? 4. So 3, 4, W6. So what is the size of this matrix? 0, 1, 2, 3, 4, 5, 6. Here 0, 1, 2. So 6 into 3. Sorry, 7 into 3. Okay, 7 into 3, it means 21. So I require only 21 memory spaces. But if I represent it using this adjacency matrix, I require 25 memory spaces. 25 is greater than 21. So one is a less spaced representation. We can say this is less space representation of the matrix. Okay, so this is the representation of the sparse matrix. This matrix is called sparse matrix. Why this is called sparse matrix? Because in this matrix number of zeros are very high than the number of non-zeros, and this is for general term. If it satisfies this type of formula, that the representation for this particular adjacency matrix, the size required to represent this particular matrix, if it is greater than this type of representation, then we say that this matrix is sparse matrix, and I have already written the formula. Okay, and how to represent this type of sparse matrix for less space requirement? This is the representation, a 3-column matrix where first column will represent what is the actual size of the matrix. Why this is required? Because ultimately we have to convert this matrix. We are storing this one, we are storing the matrix in this form in our memory. But when we will try to access, or we try to implement, then in some algorithm, then we should require this type of representation. So what we will do, from this memory, this representation, we will go to this representation very easily. Okay, to represent from there to there, we require the first column. Why? Because we need how many rows and how many columns are there. Means here how many rows and how many columns is representing actually number of nodes. Okay, and this is number of non-zero values. So these are very important to convert it from this to this. See, this is very simple. So this is now first we will try to understand how to convert from there to there. This is the first thing, how to convert. we will read this matrix one by one like this. For I equal to 0, I less than R, I plus plus. This is the for row. Then inside this the column j equal to 0, j less than c, j plus plus. Okay. Then inside this we will check if a of ij, if a of ij is not equal to 0. Okay, if it is not equal to 0, it means this is a non-zero value. Okay, before that, suppose this matrix, this particular matrix is say X matrix, this one, and suppose this matrix is A matrix, this is A matrix, and now we will store it in a X matrix. So the first we will store in the X matrix the 0 0 with R, then x of 0 1 with say c. Okay, this two value 0 0 and 0 1, this two will represent for this X matrix, this two will represent number of rows and number of columns. See, number of elements we are not calculating here because we are using one say counter variable which is initialized with 0. Whenever there is a non-zero value, it will be increased. Okay, now see, when I'm getting one non-zero value in this if part, when I'm getting some non-zero value, so this is the non-zero value for which row I, for which column j. So what we will do, we will do it like this. So better counter initialized with 1, and from that we will easily calculate the value. Counter is initialized with 1, then here we will put x counter 0 equal to I, the row value, then x counter value now initialize with 1, so x1, see this is x1, then x11, this two will be initialized with I and j value, then the next element, this will be initialized with the weight value that is in this particular node. Okay, and after that what we will do, we will increase the count plus plus. Okay, in this way we can easily create this. Only one thing is left, that is the x of 0 2 is left, which will be initialized with the value of counter minus 1, because after increasing in this way counter, once counter will be counter will become 7, it will stop. When it will stop, counter becomes 7, so that's why I am decreasing it and storing it. So this is the conversion of the adjacency matrix to this 3-column matrix representation, and we can also convert it from there to there. Okay, so this is your home task, that how to convert the 3-column sparse representation into an adjacency matrix. This is your home task. Please try this. Very simple. See, you have to read this matrix X. First, this two will give you the actual size. From that, you can easily dynamically create your array. Then, from this value, you will store the whenever this value is matches. Whenever this ij is matches, then at that position you will have to put this value. If this i0 is not, ij is not matching, then you have to put 0 at that position. So in this way you can easily convert from there to there. Okay, so this is one interesting representation of graph where number of zeros are very high for this adjacency representation. Similarly, we can create adjacency list. The linked list representation is called adjacency list. The adjacency list representation is again very simple. There is a graph like this, same like this, and I am using directed concept to minimize the representation. Minimize the representation. This is A, B, C, D, E. Okay, so it will be like this. There will be one starting starting pointer which will start. So this is the first node. Okay, this is the first node. Then we will represent the nodes which are directly connected to this particular node. See here, A is directly connected with B and C. So first we will give B, then we will give C, then null. Then see, this is a two pointer node structure, so this will go for the next vertex. So one by one I am representing the vertices. Okay, for B, now I will represent for B. Here I will give the nodes which are directly connected with B. If this is an undirected graph, then A, B possible, similarly B to A also possible. But since it is a directed graph, so it will be like this. From B only E is possible. So E is the direct neighbor. You can say what we are representing here, we are representing the neighbor nodes. Okay. Then it will go for the next vertices, vertex C. From C there is D and E. So D, then E. Okay. Now see, this adjacency list is very important for graph traversal. We will next we will discuss about graph traversal technique. So next D, for D there is only one, that is B. Okay, then null. Then comes the E. For E there is no element, so directly null, and this pointer also null. So this is called adjacency list linked list representation of the graph structure. Okay, now the next thing that we will discuss is graph traversal. This is very important. Graph traversal, just like tree traversal, in order, pre-order, post-order. In case of graph, there is a two different traversal techniques. One is called DFS, another is called BFS. Very interesting, DFS and BFS. The algorithms are very simple. If I will only discuss the idea of the algorithm. So one is called depth first search, or DFS. Another is called breadth first search, breadth first search, or BFS. This two traversal technique also can be applied in case of tree also, DFS and BFS. Okay, now the interesting thing, this two graph traversal technique is also used to other data structure. For depth first search we use stack data structure, and for breadth first search we use queue data structure. So how to remember for which we have to use stack and for which we have to use queue? See, in case of depth DFS, there is a term depth. Now you remember that in stack the structure is like this, a box. So there is some depth in the box. So for depth first search we will use stack data structure, and for breadth first search we will use queue data structure. Okay, now see how to calculate this. So suppose this is a tree structure, a graph structure. See, we can use this DFS BFS for tree structure also. Remember this. Okay, so suppose this is a a B C D E. Okay, I am using undirected graph. So first what we have to create, we have to create almost like adjacency list. So it will be like this: first node, then comes its neighbors B, C. Okay, then the for B, what are the neighbors? For B the neighbors is, now how to represent this name? In some books the names are represented in alphabetic order, but normally what you should do, so this is not the actual way. So normally what we should do, we first represent the left child and then the right child. Suppose this is the root. Consider this is the root node. Okay, so this becomes the left child and this becomes the right child. So we will represent them from left to right order. This is the best way. Okay, in some books the name of the neighbors is represented in alphabetic order, but better way represent them from left to right. So if this is the root, this is the left child, this is the right child, so it will be C then B. These are the two neighbors. Now for B, now if this is B, this is B, then this is the left child, then this is the middle, then this is the right child, left to right order. So for B, the sequence will be A, then D, then E. I hope it is clear. For C, if we consider C, so C, if we think C, then this side, this one for C, this side is the left and this side is the right. If we put C in top, and then this one is the left one and this one is the right one. So the sequence will be like this: E, then D, then A. Okay, for D, if this is D, this one is the left one, this one is the right one, so sequence will be CB. For E, if E is this one, then this is the left side and this is the right side, so for E the sequence will be B and C. So how I am representing the neighbors? We are representing the neighbors from left to right order. So this is your, you can say this is your adjacency list. I'm not drawing exactly list structure, but this is the adjacency list for this particular graph. Now if I want to apply, say first suppose I am going to apply say DFS. Now we already understand that for DFS there is depth, so we have to use stack data structure. So this is my stack data structure. Okay, now so traversal, what is the meaning of traversal? The meaning of traversal is we have to visit each and every node once. Okay, that is the meaning of traversal. So where we will start from the first node. If it is given that this is the starting node, then you have to write that node first, then the other nodes. If it is not given, then you can start from, generally we start from left top. Okay, left top corner is actually used as a starting node. So A is the starting node. So in DFS, what is the logic? So we are first visiting A. We are first visiting A. Then what we are doing? We are pushing the neighbors of A. We are pushing the neighbors of A. So this is already visited. Then we are pushing the neighbors of A. So first C will be pushed, then B will be pushed. No more neighbor is there. So now we will perform the pop operation. So which one will be popped? B will be popped. If B is not already visited, then B is the next element. Okay. Then what we will do? Now I am in B. B is the next element. So I will push all the neighbors of B which are not already done. So A already done, D, E not done. So D pushed, then E pushed. Next, again I will perform the pop operation. So E will be popped. E is not present here, so E will be visited. Then we will now in E. The neighbor of E is B and C. See, B is already done. C is already in the stack. So we are not going to push this two element. So those elements will be pushed which are not visited or not in stack. Okay. So then we will pop D. Next element D will be popped. D is not visited. So D is visited. Then what we will do? We will push the neighbors of D, C and B. C is already in the stack. B is already visited. So then we will pop next C. C is popped. So now we are in C. Then what we will do? We will push the neighbors which are not visited or not in stack. E already visited, D already visited, A already visited. So there is nothing in the stack and I have already visited all the nodes. So this is my DFS traversal sequence. So very simple. push the first one, or from first node it is the visited node, then from first node the neighbors will be pushed, then according to the pop operation you will pop one by one, those elements will be visited and its neighbor will be pushed again. And how these neighbors are pushed: if it is not visited and not already in the stack, then it will be pushed in the stack. Okay, in this way we will get a DFS sequence. How to get the BFS sequence? We know for BFS sequence we have to use the queue data structure, which is actually run in a first come first serve basis. So first A will be visited, then the neighbor of A which are not visited and not in the queue will be inserted. So first C is inserted, then B is inserted. Okay, then we will delete. Which one will be deleted first? C. So now the next element that we will visit is C. Then the neighbors of C which are not present in queue or not visited will be inserted. So E will come, okay, then D will come, okay, then A already, so not. Then the next will be deleted is B. Okay, now for B, these are the neighbors. Among this, A is already visited, D is already in the queue, E is already in the queue, so we will next delete E. So now we are in E. Now for E, B and C is the neighbor. B already visited, C already visited, so we will go for next. So D. Okay, so for D, C and B, C is already visited, B is already visited. So this is my sequence of BFS. So very simple logic, DFS and BFS. For DFS we are going to use stack data structure and we will follow the stack rules. In BFS we will follow the queue rule, and these are the two sequences. Okay, logic clear? Now see, this is very easily understood from a tree data structure, that what is the meaning of BFS and DFS. Suppose this is say A, B, C, D, E, F, G. Okay, so first we will start from the root element because there is a fixed root element. So A will be visited first, then the neighbors of A from left to right will be inserted. So B will come first, then C. Logic clear? Which one will be popped? C. Okay, then the neighbors of C, first F, then G. Which will be popped? G. Okay, G will be visited. Then there is no neighbor of G, so we will go for F. F is popped. Then there is no member of F, so then B will be popped. Okay, then for B the neighbors D and E is pushed, then E will be popped, then finally D will be popped. So how we have visited? We started from this position, then we go to the depth. See, ACG depth, ACG, then we completed that particular depth. Okay, for that, then we again going up, then again we go to the depth. For B again we are going to depth. See, B, after B we are going to again depth up to E, then D. So this is the depth first sequence. If we use breadth first, see, if we use a queue data structure, first A visited, okay, then the neighbor of A, that is B and C, next will come B. See, B, then the neighbor of B is D and E, D and E. So next C will be deleted. Okay, then the neighbor of C, F and G, F and G. So next D, then E, then F, G. So first A, breadth first search, A, then see B, C, breadth wise we are visiting. We move into this, then we move into this, and D, E, F, G. See, this is the sequence. So in depth first search we are going towards depth, in breadth first search we are going towards breadth wise. So that's why this two data structure is used. Okay, so this is the two traversal technique in case of graph data structure. There is few other things in this graph data structure. One is spanning tree, which is very interesting. From a graph, we can create many trees. See, if this is a graph, so graph having cycle. Okay. Now from this graph, if we somehow able to delete this one and this one, it will be like this. It will be like this. See, the picture is like this. So this is one spanning tree. So spanning tree means from a graph, if we want to draw a spanning tree, so from the terminology, you can easily understand that this is a tree, so there will be no cycle. So spanning tree means it will connect all the vertices but without any cycle. It will connect all the vertices but without any cycle. So this is one spanning tree for this structure. Similarly, we can draw another spanning tree like this. This is another spanning tree. See, four vertices are connected but there is no cycle. So remember, in case of spanning tree, if there, so it is a tree, so if there is a number of node or vertices is v, then the number of edges will follow the tree concept, that is number of edges is always v minus 1. See here how many, 1 2 3, here how many, 1 2 3. So edges always will be follow the tree data structure. So this is to you can create many more spanning tree from this. Okay, now from this spanning tree, if there is some weighted value is given, suppose the weighted value is given like this, weighted value given like this, then the spanning tree with minimum weight values is called minimal spanning tree. This is very important. MST, minimal spanning tree, minimal spanning tree. Okay, in uh, in your next semester you will learn different minimal spanning tree algorithms like Kruskal. This is very important. Minimal spanning tree detection. Why we use minimal spanning tree? To traverse, suppose these are nothing but the different cities, these are different cities that you have to, suppose you are a salesman and you have to visit the different cities. Okay, now see, we have visited different cities with a minimum cost, with a minimum traversal distance. Okay, that's why this type of minimum spanning tree is very important. Okay, so this is all about graph data structure.